Okay, make una do. Okay. Hello everybody. Hope we all have or had a very good evening, and you're all welcome to class. I would have to get into it immediately. For those of you that have not joined this class before, first of all, the basic principles of how to ask questions in the class is just by typing, as you noticed. There is no auditory way of asking questions. However, as the class is going on, if you come across any confusion, you are permitted to indicate by asking a question. Now, before I move ahead, I hope the audio is clear. If the audio is clear and the visual is clear, please just indicate that you can hear me so I can continue. Question. Okay. So, as I said, uh, once you get into the class, just wave so that we'll be able to continue with the class, basically. Sorry, let me do the final setup. So Okay, yeah, so let's move ahead. Yeah, thank you very much for that response. Sorry about the whole delay. Let's get into it. Now, today we are going to be getting into the part of the study in organic chemistry that deals with Iupac nomenclature generally. We will consider some basic principles and how to be able to convert names to structures and structures to name, and probably if we have the time, we would extend it into isomerism. So without wasting much time, the very first thing we are going to understand whenever you are considering naming is that we should be able to identify the different homologous series that exist in compounds, basically. So a homologous series is basically defined as a family of organic compound that possesses the same functional group. So anytime I say a homologous series, what I practically mean is a particular group of compounds that have the same properties. You could use that, because when I say a functional group is that part of the element or that part of the compound I meant to say that characterizes that particular compound. So have that in mind, that every homologous series is characterized by a functional group, and once you see that functional group, it means that that particular organic compound is attached or classified to a given homologous series. Having said that, if you look at your screen, you would notice a list of homologous series and functional groups. Now, specifically, the order of this arrangement is from the highest to the lowest. What do I mean by that? When you come to homologous series, there is what we refer to as order of priority. Some functional groups have more power over other functional groups, and once you are naming an organic compound and come across multiple functional groups, you should give one the parent chain while the other is just like a substituent. So the point is that generally when you consider a group of functional groups occurring in a particular chain, there is an order of priority. That is to say, you have greater ones and you have lesser ones, and that's the first thing we're going to be discussing in our class as we identify them. So if you look at the screen, I am going to reduce this so that I can use one side of the board. Where is it? Okay, I'm going to just reduce it. I presume we've seen it majorly. Why I want to do this is so that we can be able to follow what I am doing while I am describing. Okay, so let's go back to our board. Okay, so the very first homologous series you are going to see in that order of priority is what we call the carboxylic acid. I believe that most of us should actually have a brief understanding of this. So just have this in mind, that once you see an organic compound, let's say you have a chain of carbon atoms, and attached to that chain you notice the functional group known as the carboxylic. Carboxylic functional group is COOH. Restructuring or redrawing, C double bond OH. Once you see this particular functional group, the implication is that you're dealing with an acid. There is no two ways about it. So once I have something like this, I have CH3 COOH. The implication is that this particular compound that I have here is going to be an acid. If I have something like HCOOH, this is an acid. So the point I'm making is, once you notice a functional group and you notice that that functional group is the carboxylic group, it is an indication of the fact that you are dealing with an alkanoic acid or a carboxylic acid. I hope what I'm saying is clear. Do I need to re-explain? Hope it's clear, people. When they respond to a class on a day. Okay? So I'll have to go ahead. So as I said, the very first functional group we considered is the carboxylic group. And what do you need to know about the carboxylic group? It is characterized by the functional group known as, once you say the carboxylic group, I mean the carboxylic acid. The functional group is expressed as COOH. So you combine CO, and if you notice in my CO, it is C double bond O, and then you have the OH. Combining it together, what you have is a carboxylic group. That carboxylic group characterizes the functional group known as the alkanoic acids. So the implication is that if, for instance, you have something like this, we will still do this in naming, CH3COOH. This is what we refer to as ethanoic acid. How do I know that this is ethanoic acid? Simply because I can be able to identify the carboxylic group, which means I'm sure this is an acid. You get what I'm saying? So if you have a question, for instance, I give you a list of elements or compounds and tell you which of these is going to be your carboxylic group or is an acid. You have CH3, COOH, you have HCOH, you have CH3OH, and then you have something like CH3O. Yeah, something like this. Okay, CH3O, CH3. You will notice that option A, B, C, and D, the ones that are carboxylic or alkanoic acids are A and B. Why? Because we are able to notice, or we are able to see the functional group COOH. So once you see COOH, that's a carboxylic group and it represents the alkanoic acid. So having said that, we move to the next one. Now, if you noticed, I said that this arrangement is in a particular order, and that order is what we refer to as the order of priority. It goes from the first functional group or homologous series we need to consider, and then as we are considering it, we will keep going down and down. That is to say, I give priority to carboxylic group once it is there. See what I mean? Imagine I have COOH and I have OH. This is the alkanol functional group, which is the hydroxyl group, and this is the carboxylic group. If I am to give preference, I am supposed to consider this carboxylic group before I consider the hydroxyl group. Why? The first order or the first functional group in this order is the carboxylic group. So let's move ahead. Now, having explained that, the next functional group that is talked about in this case is the acid anhydrides. When you refer to the acid anhydrides, they are basically formed by removal of when you have a carboxylic group and you remove the OH in the carboxylic group. Once you remove the OH in the carboxylic group and attach it to something else, usually you produce your acid anhydride, especially when you are attaching let's see something like this. Let's say, for instance, you have C double bond to oxygen and C double bond to oxygen. Okay, sorry guys, there was a little I wanted to resolve something. Okay, now back to what I was saying, that when you are referring to an acid anhydride, it is basically formed whenever you remove the OH group and hydrogen, which is water basically. Okay, imagine I have something like this, C double bond O OH, and then I attach it to maybe like CH3, and then I react it with another alkanoic acid. Let's say this one is now going to be C double bond O and OH basically, and then probably I now have this attached to, let's say it's attached to CH3 too. Now if you want to form an acid anhydride, what you need to do is, after your combination, just remove one molecule of water, and the basic thing in one molecule of water is simply hydrogen plus OH. So if I'm able to take out hydrogen from one of these two and take out OH from the other, automatically I have removed one molecule of water. So the acid anhydride is formed basically when you remove one molecule of water between alkanoic acids. So I take it again. Imagine, for instance, let's redraw this. You have CH3, C double bond O OH. This is an alkanoic acid. Then you have another alkanoic acid, double bond, and then you have OH, and then you have, let's say we have CH3. Now, if we are going to form a product, remove one molecule of water means remove OH from one and remove hydrogen from the other, and then join it. What you are now going to have is going to be CH3, C, remember the double bond O is still there, then this bond that is free will now be attached to oxygen, and then it continues, double bond to oxygen, and then CH3. This is not going to be an emphasis basically in what we're going to be discussing. We will come across it later in the reactions of alkanoic acid, but I'm just saying that if you are considering an acid anhydride, it is formed by removing one molecule of water between two molecules of alkanoic acids basically. Okay, now having mentioned that, we would go to the very next homologous series, and the next homologous series that is considered there is the alkanoids. Now, your alkanoids are practically or equivalent to your esters. And how would you know an ester? So this is going to be quite easy to understand. So an ester is simply identified. It is a product, or yes, it is a product of an esterification reaction between an alkanoic acid and alkanol. We're going to discuss that in details later. But how would you know if a substance is an ester? Once you see COOH or C double bond OH, I said this is alkanoic. The esters are now formed when you remove just one hydrogen. So you have COO. This now is an ester. Once you notice COO and what ends it is not hydrogen, the implication is that you are likely dealing with an ester. This is what we refer to as the carboxylate group. So imagine, for instance, I have CH3 COOH as A, and then I have B to be CH3 COO CH3. Which one of these two is likely to be an ester, A or B? So put out your answers, A or B. Which one of them is likely to be an ester? Between the two of them, which one of them is likely to be an ester, A or B? I'm still waiting for your responses so I can continue. Which one of them is likely to be an ester? Any response? Just one response and I then continue. Okay, so obviously it is B, and yeah, Onyekachi Anyaku, you are correct. Now, as I said initially, that once you are considering an ester, an ester is produced from an alkanoic acid, but the point is, an alkanoic acid will have COO and end with H. But then an ester will end with something else that is not H. It could be an alkyl group, it could be a metal, it could be anything. But once you notice COO and it does not end with H, it is likely supposed to be representing an ester. Okay, now, what I'm going to do is the different ways of representing these particular things. I'm going to send these particular pictures to the group later so you guys can actually look through it. Now, you have that if you want to represent the carboxylic group, one of the ways is COOH. The second way to represent the carboxylic group is, sorry, let me set up my, okay, sorry about that. I need to like set my table a little bit. Yeah, okay, so I was saying something. The second way to represent the carboxylic group is, if you don't see it like this, you are going to see it like CO2H. Notice it's just like putting the two oxygens together. The other way to represent the carboxylic group is C double bond to oxygen and then single bond to hydroxyl. Once you see these two, this also represents an alkanoic acid. So the carboxylic group can either be written like this, or like this. Now, in the case of the esters can either be written as the carboxylate group, represented COO, and you have just COO without anything. Now, it means that there is space here for attachment. What could be attached here could be an alkyl group. What could be attached here could be a metal. What could be attached here could just be anything, basically. So we move on to the next way to represent it, CO2, and then you have that. Then the other one is C double bond O, and then you have O without any other extra attachments. If, for instance, eventually you have an alkyl group attached here, or a metal, or an ether, or anything, the implication is that what you have here is representing esters, while this one represents your alkanoic acids. Okay, so let's go to the next one quickly, because we're just going to run through them. Now, after your esters, the next group of organic compounds that are very important and must be noted are your acyl halides. I will not want to emphasize much about the acyl halides yet. Let's talk about them when we come to the reactions of alkanoic acid. But the point about an acyl halide is when OH is replacing an alkanoic acid. So let's leave that for now. We'll come back to that later. We go to the next one. The next one is the amide. Now, the amide group is formed by two homologous series, and I'm going to explain that. Before I get to explain the amide group, it's important that you know what we refer to as the carbonyl group. The carbonyl group is formed when carbon forms a double bond with oxygen. So this is what we refer to as the carbonyl group. Now, the combination of this carbonyl group with different other functional groups produces other functional groups. Like if you notice, in alkanoic, we combine carbonyl and hydroxyl, and it gave us the carboxylic group. But when you are dealing with something like the amide is now formed by a combination of the carbonyl group and amine group. The amine group is simply represented by NH2. So whenever you talk about the amide is produced by a combination of the carbonyl group and amine group. So just have that in mind. So if you see CONH2, another way to represent it besides this is CONH2. This is also a representation of an amide. Now, when we get to discuss amides and amines, I will now explain the different ways of representing the primary amides, the secondary amides, and the tertiary amides. Before I continue, I would like to know if you people are still following. Hope everybody is still following. Hope you all are still following the class. Just say yes if you are following. If you are following, respond. So just respond if you are following so that I can continue the class. I'm waiting for a response, just one response, and then I continue. Okay, very good. Now, going back to the screen, because if you don't understand the different functional groups and how they are represented, when we get into Iupac nomenclature, you will not understand anything. So it's best to make sure that this is properly understood. So I take it again that, as you can see, the amide group is a combination of carbonyl and amine. We will discuss that when we get to the different homologous series and discussing them in details, but I'm just trying to outline them so that you can be able to at least identify. So this is the C double bond O, and then you have NH2. The combination of carbonyl and amine gives what we refer to as amide. So that's that basically. So once you see CON, so you can see it either represented like this or represented like this. Once you see this, automatically it's an amide. Okay, so we go to the next one. Now notice the sequence now. So far, alkanoic acid is the highest homologous series. That is the one that has the highest priority and is considered first. Then we go to the acid anhydrides. And after we consider the acid anhydrides, we consider the esters. And then we go into the acyl group before we now discuss the amides. And as I said, the amide is a combination of the carbonyl group and the amine group. Once you're able to combine those things, what you have is the amide. Okay, now we go to the next one according to what we have. The next one is the nitrile group. The nitrile group is simply formed when carbon forms a triple bond with nitrogen. We are still going to discuss the Lewis structure representation of this thing and all the other things, but the point about it is this, that once you are considering a nitrile group, once you see carbon triple bond to nitrogen, the implication is that you are dealing with a nitrile. For instance, if you have a representation of let's say you have this CH3 C triple bond to nitrogen, automatically you should know that this is a nitrile. But if I had something like CH3 CONH2, this nitrile, this amide. What if I have CH3 COOCH3? What is this going to be? So this is A, B, and C. So yes, what is the homologous series of C? Respond, just one response, and then I move ahead. What is the homologous series of C? What is the homologous series of C? One response, and I move ahead quickly. Homologous series of the third guy I drew. Yes. What do we think is the homologous series? Yeah, the homologous series of C. Yes. Anyaku, you mentioned like, is it an ester? Is it an alkanoic acid? Is it an acid anhydride? What do you think is the homologous series of C? If you have no response, then we would consider moving on. Okay, good. So yes, that's correct. Why is it an ester? Because you are seeing the carboxylate group. Carboxylate is COO, ending with any other thing that is not hydrogen. But if you see COOH, then you are dealing with a carboxylic group. Okay, so let's move ahead of that and continue with the class. Now, having said that, the sequence we are noticing so far is we have first the carboxylic group, which is the alkanoic acids. Then we go down and we have your acid anhydrides. From your acid anhydrides, we went down to have your esters. Before we talked about the acyl group, and then now then the amide, and now the nitrile. So we go to the next one. The very next functional group that is following the nitrile group is the aldehyde. Now the aldehyde, the other name for aldehyde is alkanals. So aldehyde or alkanals. Now, the aldehydes or alkanals are represented by the carbonyl functional group. So just have that in mind. The functional group for the aldehydes are the carbonyl functional group. Now, there's one tricky thing about the aldehydes and the ketones. Aldehydes and ketones, or aldehydes and alkanones, both of them have carbonyl group as their functional group. Yes, both the ketones, that is the alkanones, and the aldehydes, both have the carbonyl group as their functional group. Now, this is the basic structural difference between the two of them. Once you are considering the aldehyde is characterized by a terminal carbonyl group. It is characterized by a terminal carbonyl group. And what do I mean by that? It simply means that the carbonyl group would be found at the extreme of the chain. Imagine you had something like this, 1, 2, 3, 4, and then you see C double bond O. This is a carbonyl group. I've said this before, I'm saying it again, that once you see C double bond O on its own, it is a carbonyl group. So you have that. So in this case, there's a carbonyl group here. Once you see a carbonyl group, you are suspecting two things. It's either is an aldehyde or it is a ketone. How do you differentiate between an aldehyde and a ketone? Aldehydes or alkanals, the carbonyl group would be at the last carbon atom, and that is the case here. So if, for instance, we decide to circle this out, you notice that that's the difference here. This is an alkanal. But if I had drawn something like this, imagine I had something like C, 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 and then I have the carbonyl group in between or non-terminally, automatically this would represent a ketone, while this will represent an aldehyde. It's confusing, but I hope this is clear. Students in the class, yes? Hope I was able to clarify this. Yes, just one response and then I move ahead for want of time. Okay, hope this is clear and hope this is understood. The difference between, yes, just one response. I just need one response and then I move ahead. Okay, yeah, good. Now, let's move ahead. Now, having said this, the implication of this statement is that if I want to identify an aldehyde, all I need to do is to look out for a carbonyl group. And not just look out for a carbonyl group, but to look out for a carbonyl group that is existing terminally. That is the difference between this aldehyde and a ketone. And remember, the carbonyl group is simply C double bond attached to oxygen. Moving ahead of that, we go to the next one. Now, after the aldehyde, there is another group which might not be emphasized in CHEM122. Basically, it's not one of the major functional groups discussed, but I just want to highlight it since it's on our screen. It's called the thioaldehyde. Now, the thioaldehydes is simply, instead of having the carbonyl group as C double bond to oxygen, you have it as C double bond to S. This is what we refer to as the thiocarbonyl group. So once you have C double bond to S, it's no more just the carbonyl group, it's now the thio group. As I said, let's not necessarily emphasize this because it's not part of your coursework, but just for you to know that when they say thio, most times when they say thio, it has a relation to sulfur. You get, basically. So your thio group, thiosulfate, all these thio related things have more or less a double bond relation between sulfur and another non-metal, basically. So just have that in mind, that the thioaldehyde is simply when oxygen is replaced by sulfur. But as I said, it is not an emphasis in your coursework. So let's concentrate on the aldehyde. So as I said, the aldehyde is characterized by a terminal carbonyl group. Okay, now before I even continue, I would just like to mention this, that if I have a chain of carbon atoms and then I have a carbonyl group, if I decide to fill this thing with hydrogen, in our earlier classes we decided, or we understood, that carbon atoms can only form 4 bonds. You get, which means if it has formed 1 here between these 2 carbon atoms, the remaining would be 3. So let's fill it with hydrogen. 1, 2, 3. Now we have 2 bonds here, which means it's remaining 2. 1, 2. We have 1, 2, 3 bonds, which means it's only going to be remaining 1 here, and that is 1. So you have that anytime you are representing an alkanal, because this carbonyl group would always be terminal, it always has an attachment to hydrogen. So which means if you are asked to find or represent the functional group of an alkanal or aldehyde, the functional group would simply be represented as C double bond to oxygen, which must be attached to this hydrogen. Why? Because this is the last carbon, so it has to be attached to this hydrogen. The other way it is being represented is CHO, not COH. So once you see this or this is an indication of an alkanal. Okay, so with this said, we would have to go to the next one. Before that, let me quickly rearrange, sorry, so that we'll have an effective class. I need to correct something. Okay, so we're back. Sorry, I had to do a little bit of a rearrangement so that the board can accommodate more things. Okay, having said that, we go to the next one quickly, and the next one is ketones. I have mentioned it. Both ketones and aldehydes have the functional group of carbonyl, but the difference between a ketone and an aldehyde is that a ketone will now have a non-terminal carbonyl group. So ketones, the other name for ketones are alkanones, and their functional group is non-terminal carbonyl. So how is that going to be represented? You must have carbon atoms surrounding the carbonyl group. That's what once you see a carbonyl group and then on this side there's carbon, on this side there's carbon, it doesn't, like, the number of carbon atoms on both sides can be anything. It can be 1, 2, 3, 1,000, it doesn't matter. But the point is, make sure that the carbonyl group is attached to group of carbon atoms on both sides, and automatically what you have is a ketone. So this is a ketone. So just a quick illustration or question. If I have something like this, and I have something like this, so between A and B, which one of them is an alkanal? Which one of them is a ketone? Which one of them is an alkanal? Let me fill the, yeah, just put that hydrogen there. So yes, between A and B, identify the alkanal and identify the alkanone. So we can move ahead. Do that quickly. Is A the alkanal? If A is the alkanal, you put A alkanal. If B is the alkanal, you represent that for two of them. Quickly, yes. So let's do that quickly. Which of them is the alkanal and which of them is the ketone? Just one answer and I continue. Which is the alkanal and which is the ketone? Okay. Okay, A is the alkanone, yes. That's correct, which means B is the alkanal. Good. So, Anyako, nice work. Very good. So let's continue. Let's continue. Now, having been able to identify that, we would move on to the next part of the name. And the other, after you have, I take it again, let me just run that down. The highest priority is alkanoic acid. From the alkanoic acid, we have the acid anhydrides. From the acid anhydrides, we have the esters. From the esters, we have your acyl group. From the acyl chlorides or the acyl group, we go into the amides, the nitriles, the aldehydes, the thioaldehydes, but I said it's not an emphasis here. Then we have the ketones, and we also have the thioketones. But let's not emphasize on that. So we'll go to the next one. The next one is alkanols. Alkanols. You can also refer to them as alcohols. So alkanols, alcohols, whichever one, they still represent the same thing. The functional group for alkanols or alcohols is the hydroxyl functional group. The hydroxyl functional group. So the hydroxyl functional group is simply OH. So once you have OH attached to a chain of carbon atom independently, directly, once OH is directly attached to a carbon atom, independent of any other functional group attached to that particular carbon atom, you have that OH is a hydroxyl group and it represents alkanols. So what do I mean by that? If I have C, 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 and I have OH attached, and I have C, 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 and I have O and OH attached, and I have C, 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 and I have O, double bond O attached, and then I have H here. Now, if you look at these different structures, let me see if my screen, oh yeah, it didn't cover it. Okay, so let's continue. So if you look at these diagrams, A, B, and C, automatically A is the alkanol. How do I know? Because hydroxyl group is directly attached to a carbon atom, and this carbon atom does not have any other functional group attached to it. So automatically this A is the alkanol. B, you see COOH, so automatically B is the carboxylic group. And then C, which has C double bond to oxygen existing terminally. Once you just see a carbonyl group is C double bond O and is existing terminally, automatically you are dealing with an aldehyde, which is also referred to as an alkanal. So that's that basically. So I'm just trying to identify the different functional groups so that when we get to the rules for naming, I would not have to be re-explaining these things. Once I put out the structure and you look at the structure, you should be able to identify the functional group of this element, and from there we build up to the name. Now, after we have gotten or taken the alcohols, the next thing we should take or consider is the amines. The amine functional group is simply NH2. We'll do this as a complete study as we go further in this in our coursework for this whole session. But just have that in mind that amine is actually produced from ammonia. How do you get amine from ammonia? Replace one hydrogen in ammonia with any other thing and you have an amine. So once you remove one hydrogen automatically this is now an amine. So once you are looking or considering, you are looking out for an amine or considering an amine, just have that it is represented by nitrogen attached to 2 atoms of hydrogen. Now, when nitrogen is attached to 2 atoms of hydrogen, it is specifically referred to as a primary amine. Let me just run through that. Now, as I said initially, amines are produced. Amines are produced from ammonia, and we have that this is ammonia. Once you replace an atom of hydrogen, you have started producing an amine. Now, if one hydrogen atom is replaced in an amine, this is what we refer to as a primary amine. If 2 hydrogen atoms are replaced, what you are going to have is a secondary amine. And in a situation where 3 of the hydrogen atoms in ammonia are replaced, you now have a tertiary amine. So this is primary, this is secondary, and this is tertiary. So I take it again. A primary amine is produced when 1 hydrogen is replaced in the ammonia molecule. Secondary is produced when 2 hydrogen atoms are replaced in the ammonia molecule. And then a tertiary is from when all the hydrogen atoms are replaced in the ammonia molecule. We're still going to discuss this in details, but I'm just trying to help you understand this. That basically, once you are considering an amine, it is produced by replacing the hydrogen atoms in ammonia. So, as I said, after you consider the alcohols, before you now consider your amine. So basically, your primary amine is one of the most popular amines we are going to be considering, and it is represented by the functional group NH2. So once you see NH2, if I have this, okay, just quick question, which one of these two is an amine? Which one of these two is an amine? Oh, no. Which one of these? Okay, 3. A, B, C. So amongst A, B, C, which one of them is an amine? Which one of them is an amide? And which one of them is a nitrile group? Just a quick question before we continue. Yes, just one answer and then I move ahead. Which of these is an amine? Which of them is a nitrile? Which of them is an amide? Once I have an answer, we just move ahead basically. Okay? Okay? So just one answer. Oh, C. Yeah, that's that basically. So the C is, I presume what you mean is that C is an amine, right? That's Onyekati and Yaku. Okay. Okay, so let's move ahead. So, having been able to identify the amines, the next functional group we are going to consider after the amines is the ethers. Now, your ethers are more or less referred to as your alkoxides. I take it again. Your ethers are referred to as your alkoxides. And what do I mean by the alkoxides? It simply means that you have an alkyl group attached on both sides of oxygen. So the ether, another name for the ether is the alkoxides. So once you have oxygen and you have different alkyl groups or different groups attached to both sides of oxygens, what you refer to this as is an ether. Take for instance, you have CH3 here and you have CH3 here. This is what we refer to as dimethyl ether or methoxymethane. So you notice that oxygen is in the center and then 2 different groups are attached on both sides. Then what do you refer to this as? You refer to it as an ether. Basically, it's not like a major amongst the functional groups we are going to be studying. The homologous series we are going to be studying, the ether is not like a major, so I have to move ahead. Now, moving ahead, the next one that is going to be considered the sulfide. Let's do the sulfide because it's not major. Now, I am just taking this thing in a particular order. Let's take the order again. The highest priority or the functional group of highest priority is the carboxylic group for the alkanoic acids. After that, you consider your acid anhydrides. After that, you consider your esters. After your esters, you consider your acyl halides. After your acyl halides, you consider the nitrile. After the nitrile, you consider the amide. After the amide group, you now consider the alkanals. The alkanals to the alkanones, the alkanones to the alcohols, and from the alcohols you consider the amines before you come to the ethers. Now, after you have considered the ethers, that is when you will begin to consider the alkenes. Now, alkenes are simply described as hydrocarbons. Hydrocarbons, I'll just call them HCs. HCs, that's hydrocarbons that possess double bond between carbon atom. Between carbon atoms. So once you have and you notice the double bond between carbon atom, automatically you are referring to as that is identified as an alkene. I don't think I have to buttress the type of hybridization, but just a throwback to this. Once you have this, what type of hybridization is represented here? To anybody in class? Yes? Just, a review of what we've been doing. Yes, what type of hybridization are we considering? Yes, just one answer. What type of hybridization are we considering here? Just put out your answer. sp2, and that's that. Yeah, makes sense, makes a lot of sense. Okay, so let's continue now. Yeah, where was I? Yeah, back to the screen. So let's continue. So that's the no, did I say you consider the alkenes first? No. Oh yes, the alkenes are double bond basically, but before you consider the alkenes, you are supposed to consider the alkynes. So let's go back a little bit. Alkenes have been explained. The alkynes are basically hydrocarbons with triple bond. Alkynes are hydrocarbons with triple. So once you have triple bond between carbon atom, that's an alkyne. I don't think this is so much of a rocket science, it's just basic. Triple bond between carbon atom, you have that as an alkyne. If I have carbon, 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 and then I notice a triple bond anywhere between carbon atom, automatically that compound is referred to as an alkyne. Okay, so with that said, we go to the next one. Now, after you've considered your alkynes, then you consider your alkenes. That is when you now go to your halogens and the rest of them. But this basically is the order of priority for organic compounds. Now, with all this said, we have identified the different functional group, and I'll just run through one classwork. I'll write a list of compounds, just draw the structures of a list of compounds, and you identify each of these compounds. So you just identify the homologous series of the compounds. So I have A. You just that is to say, you say A, you tell me what A is. B, you tell me what B is. I'll just write like 5 of them, just identify them basically, just to review what we've been doing. So that's CH3, COOH, B, CH3, CO2, CH3, C, D, and finally E. Okay, so quickly do that, send out your answer basically for these compounds. Each of these compounds identify their homologous series basically, so we can continue. Okay, so sorry about that. I wanted to just put out something. Yes? No answers yet. Okay, yes. A alkanoic, let's review that. A alkanoic, yes. B is, what did you write there? Ester, correct? C is nitrile, D is alkyl, and E is amide. Yeah, makes sense. That's correct. So let's move ahead. Now, having said this, we go into the next part of the study. Now, please, before I even get to that, I just want to run down the order again. The order of priority, first of all, is your alkanoic acid. So once you see the carboxylic group, the preference, or that has to be what you consider the compound as. So what I mean by that order is, imagine for instance, you have this. For instance, you have this. Let's put this. And then you have COOH. And then you have OH. Is this compound going to be referred to as an alkanoic acid or an alkanol? Remember, OH is null, while this is alkanoic acid. It's going to be referred to as an alkanoic acid. Why? In the order of priority, alkanoic acid is considered above hydroxyl. I hope this is clear. So once you have a group or an organic compound that has multiple functional groups, and you have that the alkanoic acid is there, that compound is an alkanoic acid. So even if I have something like this, NH2, and I have COOH, this is basically your 2 amino acid, or 2 aminopropanoic acid. That should be the alanine, basically. So if you look at this compound now, what do we think is this compound? This is an alkanoic acid. It's not an amine. It's an alkanoic acid. Why? The carboxylic group has higher priority over the amine, so the compound is going to be referred to as an alkanoic acid. If, for instance, probably you had something like this. Let's say you had NH2, and probably you had maybe like chlorine. This is an amine. You get why? Because the amine group has a higher priority over the halogen group, or chlorine. Halogens are your any elements in the group 7. So the amine group has a higher priority over the halogen. So you will not refer to this as a halogeno compound. What you're going to refer to this as is an amine. Basically, you would say it is a halogen substituted amine. Why? In the order of priority, amine is higher than the halogens. Okay, so let's leave that and move ahead. Now, having represented this, the next part, okay, sorry, I was listing out the order again. So we said you have the alkanoic acid, just for re-emphasis. After the alkanoic acid, you have your acid anhydride. After the acid anhydride, you consider your esters, you consider your acyl group, then you consider the nitrile, and then you consider, before the nitrile, you should consider the amide group. So you consider the amide group, then you consider the nitrile, and after the nitrile, we can now get into our alkanals, our alkanones. After the alkanones, we can consider alcohol. Before we consider amine, then we could now get into the ether and talk about the alkyne, then the alkene, and then finally the haloalkanes and every other thing. So basically, the thing about this is, make sure you have this order in your head. Try as much as possible to go through these things over and over and over, such that you have these things in your head, because once you are going to name an organic compound, if it has multiple functional groups, you would need to be able to represent the differences between these functional groups. Okay, now with that said, the next part of the study we are going to get into is the parts of an organic name. So once you have an organic compound will be represented by different parts, and we're going to consider 3 major parts of an organic name. The parts of an organic name include, that is according to my own study, is the prefix. The second one is the infix, and then finally you have the suffix. So we're going to be taking these things and understanding them differently. Before that, let me just take this out of the screen quickly. Okay, yeah, okay. So as I said, once you are considering the name of an organic compound, there are three major parts. The name of an organic compound is made up of three major parts, and those three major parts include your prefix, your infix, and then your suffix. So let's explain this basically. Let's start with the first one, the prefix. The prefix is simply described as the part of the organic name. The prefix is the part of the organic name that indicates the substituents. Substituents are simply attachments to the parent chain. Anything that is attached to the parent chain is referred to as a substituent. So if I have an organic compound, let's look at this organic compound now. COOH. We know that this is an alkanoic acid. But take for instance, chlorine was attached here. Automatically, this chlorine becomes a substituent to the parent chain. The parent chain has the functional group. So you have that this chlorine here is now a substituent. Now, having explained that, the question is, how do I represent a substituent? And how to represent a substituent is as a prefix. Let me, for instance, put down the name of this compound. This compound is going to be represented as 2-chloropropanoic acid. 2-chloropropanoic acid. This part of the organic name that represents the substituent is what we refer to as the prefix, basically. So you have that. Quite easy to understand that the prefix simply represents the substituent of attached to the parent chain. And if you notice, the prefix comes before the main name, which is the parent name. Okay, I hope that is clear for those of you still in class. Do I need to re-explain? Just one response and I continue. Hope it's clear. Hope what I explained is 100. Just one response and I continue. Yeah. Okay. Yeah. So let's continue. Good. Now, having said that, we move ahead. So we've talked about the prefix, and I said that the prefix basically represents every substituent attached to the parent chain. Next part of the organic name is the infix. Now, this infix is very important because it is actually the part of the parent's name. The infix is simply described as the part of the organic name that indicates the number of carbon atoms. It indicates the number of carbon atoms in the parent chain. So once you are considering an infix, it is a part of the organic name that indicates the number of carbon atoms in the parent chain. Let's explain that to help. Let's put this put up an illustration to help us understand that. So if I have, for instance, let's use the other example we had COOH, and then this is a substituent. Now if you notice, the main chain of carbon atoms is 1, 2, 3. Why? The functional group here that we know is the orgapata is carboxylic group. Any other carbon atom attached to the carboxylic group automatically becomes part of the parent chain. So which means if I circle this out, this is my parent chain. This particular guy now is a substituent. So if I want to represent, this is a substituent, while this is the parent chain. So I now said something, that the infix is the part of the organic name that will tell me the name or give me the number of carbon atoms in this parent chain. How will it do that? Now, I'm going to give us a list of infixes that represent specific carbon atoms, and with that, it will make it easier for us to understand. So let's look at the list. I'm going to put down the number of carbon atoms. These are some of the things that must be put to your head, that is, you must understand them, and then the infix. So if you have one carbon atom in the chain, one carbon atom the infix is met. So which means if I have COOH, I know that this is an alkanoic acid, but because I have one carbon atom in this particular alkanoic acid, the name of this alkanoic acid will become metanoic acid. If I have two carbon atoms in the chain, it is eth. So when I have CH3 COOH, how many carbon atoms do I have here? 2. So what do you think is going to be the name of this compound? So yes, Anyaku, I guess you are still with me. Onyekachi, yes. What is going to be the name of this organic compound? Okay. Okay. Yeah, for want of time, basically, because we can see that this is 2 carbon atoms, we have that the name of this organic compound will now be ethanoic acid. Why? The number of carbon atoms is 2, and the infix that represents 2 is eth. So if you put that together with the alkanoic, you could say eth-alkanoic, but you don't say eth-alkanoic, you just say ethanoic acid. Why? Because the infix 2 represents these things. Okay, so let's move ahead, move it up. Now, once you are dealing with, so yes, as I said, 2 carbon atoms represented by eth, 3 is represented by prop, 4 is represented by but. So once you have 4 carbon atoms is but, 5 is represented by pent, 6 is represented by hex, 7 is represented by hept, 8 is represented by oct, 9 is represented by non. Okay, so let's like number of carbon atoms, then infix, and then 10 is going to be represented by deck, 11 is represented by on deck, 12 is represented by do deck, 13 is represented by tri deck, 14 is represented by tetra deck, 15 is represented by penta deck. So you could actually notice a sequence here that once you have your multiples of 10, they usually have special names. All you need to do is attach the Latin name for the other numerical values to that multiples of 10, and you have the name for the corresponding one. So the point is deck, on deck meaning 1 and 10, do deck meaning 2 and 10, tri deck meaning 3 and 10 basically. So 16 is going to be hexa deck, 17 should be hepta deck, 18 is going to be octa deck, 19, okay, I bought space, okay, I still want this to be on the screen, so let me just do a little bit of wiping. Take this out. Okay, then continue with yeah, okay, yeah, I bought. Okay, so yeah, so back to what I was doing. So which means 19 is going to be referred to as nona deck, while 20 is represented as icos basically. So the point is, if you have 20 carbon atoms and it is an alkane, it will be icosane. If you have 12 carbon atom and it is an alkanoic acid, it will be dodecanoic acid. So these names represent the number of carbon atoms in the parent chain. Having said that, I presume this is understood basically. Yeah, I hope this is understood. Whoever is in class. Okay, so for want of time, we would have to move ahead. Now these represent the infixes, and infixes tell us the number of carbon atoms in the parent chain. You get it can actually be used to represent number of carbon atoms generally, but as a part of the organic name, the infix is going to tell us number of carbon atoms in the parent chain. So which means if, for instance, I have a chain of carbon atom 1, 2, 3, 4, and then I have double bond O to H. I know that this is an aldehyde, but this aldehyde has how many carbon atoms? 1, 2, 3, 4, which means the infix I'm going to use to represent this is boot, basically. So you have that in mind. Let's continue though. Now, the final part of the organic name that I'm going to describe is the suffix. Now, the suffix is one of the most important parts of the organic name. In fact, every part of the organic name is important, but this suffix is what indicates the homologous series. The homologous series. So the suffix is what indicates or tells us what homologous series is existing. You get. So what do I mean by that? If I happen to put down a structure and notice that that structure is an alkane, it means that, before I even get to that, the suffix is also the last part of the organic name. So once you have the ending of the organic name, the ending of the organic name is the suffix. So back to what I was saying. Now, an alkane would have a suffix ane. An alkene will have a suffix ene. So once I see double bond, it means it's supposed to end with ene. If I have an alkyne, hydrocarbon with triple bond is going to be yne. If I have an alkanol, the suffix for alkanol is ol. That's why phenol, once you see phenol, you begin to suspect that there is like connection. Okay. Just wanted to, I hope we are back. There was a little bit of, we lost connection at some point, but let me quickly confirm that we are still live. Let me quickly confirm that we are still live. Yeah. Okay, so yeah, we're still live. Let's continue. Sorry, I had an interruption in my network, so I wanted to confirm that we still did. Okay, so having explained this, moving ahead to what I was saying initially, the alkanols are represented by the suffix ol. So once you see a compound and it ends with ol, you begin to suspect that that is an alkanol. Okay, we have the aldehydes. The aldehydes or alkanals. The suffix of the aldehydes or alkanals is al. So once you see a compound, propanal is an alkanal, is an aldehyde. If you have the ketones or alkanones, the alkanones or ketones, their suffix is one. So once I have propanone, acetone is a ketone. You should know that basically, and that's how it works. Then my alkanoic acids, or your carboxylic acids, are represented by the suffix oic. So which means if you see C double bond OH, the implication, C double bond OH, the implication is that it is an alkanoic acid, which means the last part of it should end with oic. Then we go to the next one. I'm just putting down the major ones we need to know. Amine. If it is an amine, it should end with amine. The suffix for amine group is still amine. Same thing with amide group. The homologous series amide is also represented by the amide as a suffix. If you have same thing with the nitrile, like propionitrile, nitrile. Okay, if for instance we are dealing with the ester, the ester ends with OH. So once you see methyl methanoate, methyl methacrylate, methyl propanoate, once you hear OH, it's an ester, most likely. These are the major ones though. We'll be discussing as many as we go further in the naming. We'll be identifying some other ones. But basically, These are the major suffixes that you need to know. So once you see an alkane, or you know that this is an alkane, it means that it should end with ANE. Okay, having said that, let's just look at this one exercise basically to help us understand this. What is the suffix for the following compounds? What is going to be the suffix for the following compounds? Okay, so what's the suffix for the following compounds? I'll answer this one. The suffix for this one is amine. So what's going to be the suffix for this one? Yes? Students in the class, quickly answer. Okay. So yes, what's going to be the suffix for B and C? What do you think? The suffix for B and C. Okay, sorry, I've been having a little break in transmission, but I think we are still live, right? I guess we are still live. Okay. Yeah, if we are live, please just comment so I'll know. Basically, I think we are still live. Yeah, so let's continue. Now, okay, yes. So A is amine, B is ane, and C is all, which are all correct. So yeah, so let's continue. Moving ahead, I will go to the next part. Now, we are done with the major part of this thing, and the major part we are done with is the part of the organic name. The next part we are going to get into is the rules for naming organic compounds. Now, we are going to be looking into 8 different rules and how they are applied, and with that we'll be able to understand the basic principles behind naming organic compounds. Okay, so let's take them one by one. The first rule we can see on the screen is this: when naming unbranched alkanes. Okay, so have this in mind. In naming, the very first thing that you need to understand how to name is an alkane. So once you're able to understand the naming principles behind an alkane, it is easier to navigate through naming other organic compounds. So that's why in the rules I'm going to be emphasizing alkanes. However, I will now show how the application or the understanding of your application of the naming of your understanding of the principles behind naming alkanes can be applied to other homologous series. Okay, so let's continue. Now, when naming unbranched alkanes, attach the infix which corresponds to the number of carbon atoms to the suffix ane. What does that simply mean? Let me take this out of the screen so that I can be able to represent that properly. So let's look at the board. If, for instance, you have an alkane, how do you know that it's an alkane? When it contains only carbon and hydrogen, and then there are only single bonds. But before I even get to that, if you notice, they said unbranched. Let me just represent something. If you have a straight line, you have a curved line, and you have this line like this, and then another line straight like this. This is A, this is B, this is C, and this is D. This is a continuous line. It is a straight line which is also continuous. B is not branched. B is simply a continuous line that is curved. C is not branched. C is simply a continuous line that is bent. The only branched line in this case is D. So when they say branched, the implication is that it is an extension of a continuous flow. When you hear the term branched, as I said, it is simply an indication that you are dealing with an extension of a continuous flow. So if you have that a particular chain of carbon atom was continuous, but then it started turning towards different angles, it does not mean that it is branched. For you to refer to it as branched, there must be something extending from the continuous flow. So I had to emphasize this because of that rule. The rule number 1 says, let me put it up to the screen again. Rule number 1 says that when naming alkanes, not just alkanes, but unbranched alkanes, attach the infix which corresponds to the number of carbon atoms to the suffix A and E. So let's look at this particular structure to help us understand that. So imagine we had something like, let me remove this. So imagine we had something like carbon 1, 2, 3, 4, 5. This is CH3, H2, 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 and H3. Now, the first thing is to identify what functional group this thing is. And as I look at this thing, I'm seeing a hydrocarbon that has only single bonds. Once you notice a hydrocarbon that has only single bonds, automatically it is an alkane. Now, they said if you want to name it, this is not branched, this is continuous. Even if I had drawn it like this, it is still not branched. It is simply bent. For me to refer to it as branched, there has to be an extension of this is just a continuous flow. If I had, for instance, maybe attached something like this, I can now say that this is branched, that this is the continuous flow and this is an extension. But once you have something going on continuously, the highest you can say is that it is bent or curved. But once it is continuous, it is unbranched. So let's continue. If I'm to name this thing, the principle said that we should attach the infix which corresponds to the number of carbon atoms. So let's count 1, 2, 3, 4, 5. The infix for 5 is pent, and we should attach it to the suffix A N E. So this is pentane. Now imagine, for instance, it was not an alkane. Let's say we had C, 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 and then this is O2H. What is this now going to represent? Count the carbon atoms. 1, 2, 3, 4. It's continuous. It's not branched or substituted. You have that is 4 carbon atoms, and 4 is represented by but. Because the suffix is an alkanoic acid, this is going to be butanoic acid. Now let me say one or two things about what I did here. If you notice, between every of these carbon atoms you have single bonds. That is exactly why I refer to this as but. It's supposed to be butane. But because of this COOH now, the E is going to now be replaced. And if this E is replaced, you will have that you are going to replace it with the actual name of the functional group. And we said that once it is a carboxylic group, the suffix for this carboxylic group is going to be oic. Remember, why it is butan is because everything is single bond. If I had a double bond somewhere here, it will be butene. If I had a triple bond, it will be butene. So basically the principle is, once you are able to identify the infix, you have that is but. If it is only single bonds, you continue ane, but then remove the E and then replace it with the corresponding suffix for that functional group. So in this case, it's alkanoic, and the suffix for alkanoic is oic. So this is but and oic. Okay, you try this. Imagine you have something like this. Let's say you had CH3 C double bond OH. Okay, so what do we think? What's the name of this compound? Yes? What's the name of this compound? What do we think? Based on what I explained, what do we think is going to be the name of this compound? Do that quickly so we can move ahead because there's no time. Do that quickly, we still have a lot. And I want to put out as many illustrations as possible. Okay. Methanol. Nah. Didn't you see that there are 2 carbon atoms there? So we check your answer. The infix for 2 carbon atoms. Yes, you also include the carbon of the functional group. I probably did not mention that. But yes, you are supposed to include the carbon atom of the functional group. So change. Your answer is not going to be methanol. What do you think it's going to be? Exactly. So it's going to be ethanol. Why? You confirm that this is an alkanal. How do you know it's an alkanal? You are seeing terminal carbonyl. And once you notice that, automatically, naming is going to be very simple. So you count the number of carbon atoms, 1, 2, and then attach it to the corresponding suffix. That's all you do. So that's going to be et, an. And because it is an alkanal, it's going to be ethanal, basically. Okay, very good. Let's go to the next rule, basically. So yes. So having mentioned that, we go to rule number 2. So rule number 2 states that when naming a branched alkane, identify the parent chain. So the very first thing you need to do, if you notice that your alkane is branched, is to identify the parent chain. Now, the parent chain is the longest continuous chain of carbon atoms, which must possess the functional group of highest priority. So this is not just for alkanes. If you are just dealing with alkanes, you could end it with the parent chain is the longest chain of carbon, longest continuous chain of carbon atoms. However, as I said, I'm including the principles to naming other functional groups too. So if you want to identify any parent chain at all, what you need to do is look out for the longest chain of carbon atoms, which must possess the functional group of highest priority. Okay, so let's get to explain that so that we'll be able to understand it. Now, what do we mean by that statement? So let's go to our board. Imagine, for instance, I have this particular compound. For now, I'm just going to be putting out the carbon atoms to make it easier for us. You do not need to go and cram or put all these rules in your head. As you apply them, you will notice that these things would actually stick to your memory, basically, and that's how it works. Now let's start with this one. If we are going to identify the parent chain here, it is very, very simple. All you need to do is count from carbon end to carbon end, from carbon end to carbon end, and then eventually find out the longest one. Please note, this is not the last carbon, it continued to here and also continued to here. So we have 3 terminal points. We have 1 here, we have 2 here, and we have 3. So let's count from carbon end to carbon end. So let's start counting. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I'm going to use I'm going to separate this parent chain so that we can see it clearly. Now if you count, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 carbon atoms. Now I can decide to count from another end to another end. Let me just remove this. You know, the first thing you need to do is to confirm before you choose your parent chain. We found out that from here to here is going to be, that's from this dot to this dot is going to be 9. Let's check from here to here. So if we count from here to here, we're going to have 1, 2, 3, 4, 5, 6. So the point is not necessarily about counting the straight chain. Make sure you count from end to end and find the one that is the longest. So we had 9. We now have 6. Let's see if we have another number. Remember, this is an end and this is an end. So let's count continuously till we get here. This is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 10. So you notice that the first one we had was white and white, which is from here to here, and that's 9. Then the next one we have, let me use a different color, probably green or thereabout. You now have this from here to here, and from here to here is 6. And then we now have a final counting, which is from here. Let's use blue probably. You now have from here to here. And when we counted from here to here, we got 10. So remember, bringing up the rule again. Let's look at the screen. Where is it? So the rule says that the parent chain is the longest continuous chain of carbon atoms. So let's take that part first. We'll come back to the other ones. The parent chain is the longest chain of carbon atoms. We're going to be taking this thing in parts so we'll be able to understand it. So look at this screen. You will notice that your longest chain is from this carbon to this carbon. So what I'm going to do is I am going to use a line to just seclude it so that I would understand and see it very clearly that this is my parent chain. So that's that basically. Now, That is the parent chain. So if we are to name the parent chain now, what do we simply do? We notice that the number of carbon atoms in the parent chain is going to be 10. That's seen in the next rule, I think. Let's see. Okay, so I should have mentioned that. Where is it? It's actually in a note somewhere around here. Okay, now the point I was supposed to make is that you name the parent chain just as your continuous chain of carbon atoms. That's just as your unbranched alkane. So what do I mean by that? This parent chain has 10 carbon atoms and the infix for 10 is dec. Because I know that this is an alkane, single bond hydrocarbon, this is going to be dec A, and that's that basically. So you have that. So whenever you want to find out the parent chain, you count from end to end, find out the longest one, and then attach the infix to the A. Now we're not done naming this compound. This is just the parent chain. You can decide to draw this structure in your notes. We'll come back to it to name it fully. But so far, hope there is no confusion. Hope there is no confusion. Just one response and then I continue. Hope we are following. Okay, just one response and then I continue. Hope it's clear. We'll try more examples, but I just need to confirm if you are following based on what we've done so far. Yes, just one response and then I move ahead. Now, no confusion. Okay, very good. So let's continue. Now, having said this, you try this. You tell me what do you think is going to be the parent's name for this particular compound? Okay, so let's have it. You have 1, 2, 3. Let me use a different color so that I can circle it out later. Okay, so you have one. I hope nothing is blocking the screen. Let me see. Okay, yeah. So you have 1, 2, 3. Okay. Yeah, let me just okay, we have this. So yes, which one or what is the, just name the parent chain. I didn't say name the whole compound, just the parent chain. Just identify the parent chain, how many carbon atoms are in the parent chain, and what do we think is the name of this parent chain basically. So do that quickly, so we can continue quickly. What do we think? Now note to it must possess the functional group of highest priority. Notice that alkanal has a higher priority to alkane, so which means you must put that C double bond O, no matter not minding any other factor. You must add the carbonyl group to that chain, because in this particular chain the carbonyl group has a higher priority to alkane. So do your counting, and what do we think is the number of carbon atoms, and what do we think is the name? Quickly do that. Nonane. Okay, now yes, let's analyze it. Let's analyze it together. Nonane is not entirely correct, but I'll tell you why it is not entirely correct. Okay, yeah, you tried. That makes sense. Okay, it's not nonal, it's non-nanal. I will explain. Now, if we are to count the number of carbon atoms in this chain, we notice that the longest, even by merely looking at it, the longest chain is this one. Include the functional group. The longest chain is this one. So remember, let's put up that rule or that principle we said. If you look at the screen again, when we were naming or putting out the principle behind naming the parent chain, we said that the parent chain is the longest continuous chain of carbon atom which must possess the functional group of highest priority, which means as much as we are counting the longest chain, we should also bear in mind that that longest chain must carry the functional group of highest priority. There are scenarios where you have longest chain, but once they do not carry the functional group of highest priority, they cannot serve as the parent chain. You must include the functional group of highest priority before you consider the length of the chain. So that means that you must count from the functional group before you go to the chain. But remember, there is an order. There is an order of priority. So which means you're going to consider them based on that order. Okay, so let's go back to the screen. Let's take this out and then go back to the naming of the compound. Okay, so okay, I think I understand. Okay, now back to what I said. If you want to name this thing, we counted and saw that the longest is from here 1 2 3 4 5 6 7 8 9. Now the longest that contains the functional group, we would have counted from here and it would make sense, but it would not be correct. Why will it not be correct? Because it does not contain the functional group of highest priority. So just have that in mind, that when you are allocating or counting the carbon atom, you must add the functional groups of highest priority, and in this case is the carbonyl, which is for alkyl. Now the number of carbon atoms is 1 2 3 4 5 6 7 8 9, which is supposed to be none. Now because it's single bonds, we can say nonane. Now what you simply do is not to remove A and E, just remove E. Just remove E. Because this is an alkyl, I will replace that E with Al. So this is going to be non-anal. So that's that basically about this particular structure. Okay, to help buttress this point, why not you try this one? Look at this structure. What is going to be the name of this particular compound? Imagine I had something like this now. The parent chain, just the parent chain, just identify the parent chain. And probably had chain of carbon atoms that went like this. Okay. Maybe had an extension this way. So yes, what do we think? What do you think is the name of the parent chain? Not the name of the compound, but the parent chain. Just the parent chain. Identify the parent chain, just the parent chain. What's the name of the parent chain, basically? What is the name of the parent chain? Just the name of the parent chain. Yeah, I need your answer. Do that quickly. We do not have all the time in the world, basically, so we'll be able to cover as much as possible. Yes, what do we think? What do we think? I'm still waiting for our answer. Well, let's be fast about that. Oh yeah. Okay. Nice try, but I want you to check exactly. Makes sense. So you should, it's undecanoic acid. Why is it undecanoic acid? Because first of all, the functional group is not alkyl. You know, I told you that C double bond O and then OH in the same carbon is not aldehyde. It's going to be an alkanoic acid. Once you see COOH or C double bond to O and then OH or CO2H, it represents the functional group alkanoic acid. Yeah, that's nice work. So the next thing is to count the carbon atom. That's 1 2 3 4 5 6 7 8 9 10 11. 11 indicates on decane, right? But then you remove the E and put oic, and that's that. Makes sense. So you're getting a hang of it. Now please, my advice is this. If you're naming, after you've written it, circle out that parent chain. circle it out so that you'll be able to see what is your parent chain and what is your substituent. Circle it out. So make sure in your notes as you are taking note of this that you circle out that parent chain. Now if you circle it out, you will now notice that your substituents are now clear. What is your substituent? This guy here and this guy here. So basically that's that. I think I can go to the next rule. Basically there are about 8 rules and we are still in rule number 2. Okay, so let's go to the next rule. Let me put it up in the screen so that you can also see that. Yeah, so the third rule is, if there are multiple functional groups or bonds, the parent chain should possess as many bonds and functional groups as possible. What this thing means is that once you notice that there are many functional groups and there are many bonds, your emphasis should not just be on longest chain again. The emphasis should now be which of this carbon chain will accommodate as many bonds and functional groups as possible. I would use an illustration to help us understand this. Okay, take for instance, okay, let me take this out so our board will be clear. Okay, so back to the board. Now, imagine for instance you have this compound. Let's see, 1, 2. Okay, let's start with something simple. Okay, so if you look at this particular compound, you will notice something. Let's count the longest chain. The longest chain is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That is exactly the longest chain of carbon atom. However, the point is not necessarily the longest chain. The longest chain, which is going to be the parent chain, must have all the functional groups. So which means I can't count these things and omit the carboxylic group. It would not give me my parent name. So my parent name must include those functional groups. So I'm going to start from here to count and then find out which one is the longest. So counting from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11. Then counting from here still, because this is a functional group, I have to count close to it or from that particular functional group. So you have 1, 2, 3, 4, 5, 6, 7, 8. You have 11 and 8. Now, the longest continuous chain that contains this functional group is now the parent chain. If it's just the longest continuous chain that excludes it, it's not going to serve as the parent chain. Whatever longest chain that you have must contain the functional group, basically. And that is basically the principle of rule number 3. I hope this is clear. Is there any confusion? If there's any confusion, please, this is the time to ask your question. Any confusion so far, this is your time to ask your questions. Any confusion? Oh. So yes, any confusion? If none, please just indicate so we can just move ahead. Yeah, that's okay. None so far. So let's continue. Basically, so okay. With that said, just help me identify. Okay, so how many carbon atoms should be existing here? So tell me the number of carbon atoms in this particular chain. That's in the parent chain of this compound. I'm going to just put a compound and then you tell me how many carbon atoms you think is in the actual parent chain. Okay, so yes, How many carbon atoms should be in the parent chain of this particular compound? Identify. How many? Yes, give me your answer. Remember, this is chlorine, no, not carbon. This is Cl. This is chlorine, not carbon. We can use another color, right? I made the cyan. Chlorine with this. This is OH. Basically, okay. Oh yeah, how many carbon atoms are in the parent chain? How many carbon atoms are in the parent chain? How many carbon atoms are in the parent chain? Yes, still waiting for a response. 7. Okay. 7 is correct. 1, 2, 3, 4, 5, 6, 7. So you notice what you did. You had to consider the longest chain that has most of those functional group, and that is the one that would suit or become your parent chain. But in a scenario where you don't have multiple functional group, you now check for the one that has the longest continuous chain of carbon atoms. Okay, so that's that basically. So as I said, these are things that you don't necessarily need to cram. All you need to note is just keep going through different names, and as you do that, you get used to them. Okay, let's go to the next principle in naming. Let's put it out so that you can be able to see it. Okay, that's rule number 4. Okay, so the next principle is rule number 4. After you are done with knowing which one is the parent chain and identifying it, what I did with you was just to describe the different ways of identifying the parent chain. Once you are able to do that, you allocate locants to the carbon atoms of the parent chain. That's rule number 4. Allocate locants. Locants are serial numbers. So just in case you're confused, when I say a locant is simply a serial number. That's 1, 2, 3, 4, 5, 6, 7. Basically, that's a locant. So allocate locants to the carbon atoms of the parent chain, starting from the carbon end closest to the functional group of highest priority or substituent. I'm going to have to explain that for you to understand this. Now let me explain this. I will draw my carbon chain and help you understand this. Now, if I have, let me see if I can probably let me put this together. Okay, we have this. Okay, so this is a simple one. We'll take it from simpler ones to more complicated ones. Now, we already know that the number of carbon atoms in my longest chain is 1, 2, 3, 4, 5, 6. And the parent chain is going to be an alkane, which is hexane, because it's single bonds basically. Now, halogens usually occur as substituents. They are not like major functional groups, so they are usually substituents basically. Okay, so having said that, if I'm to allocate locants, I said locants are serial numbers. I'm going to start from either this end or this end. Remember, the rule says allocate locants starting from the carbon atom or carbon end. Let me put that out again so we can see that. You have to start from the carbon end closest to the functional group of highest priority or substituent. So if you are not seeing any functional group, you now consider substituent. But if you are seeing a functional group, you consider it before you consider the substituent. So let's continue. Let me take this out and then, okay, it's out. So back to what I was saying. If we are to allocate the locants are just serial number 1, 2, 3, 4. I'm not going to start from here. Why? Because if I count 1, 2, 3, 4, 5 before I get to a carbon atom, before I get to a substituent. But when I'm counting from this end, I just count 1, 2, and I'm here. So which means I'm going to start allocating my numbers from this end, and that's going to be 1, 2, 3, 4, 5, 6. So have that in mind. You allocate locants starting from the carbon end closest to a substituent or a functional group. Okay, let's spice that up a little bit. Imagine, for instance, we have this particular chain. Let's spice it up a little bit. Spicing it up a little bit. Let's say we have OH. Okay, so the students in class, am I going to be counting from the left or from the right? So tell me, am I going to be counting from the left or from the right? Am I going to start my allocation from the left or from the right? So yes, if it's left, just say left. If it's right, say right, so that we will continue basically. Oh yeah, I'm gonna talk time no day. So where am I going to start allocating from? From the left or from the right? Sharp, sharp. Are we allocating the locants from the left or are we allocating from the right? Yeah, so Abiona, don't go sleep. Okay. Yeah, exactly. From the left. Why is it from the left? Because from the left, if we have to count it from the left, you will count 1, 2, 3. You've gotten to a substituent. Sorry, this is not a substituent, this is a functional group. But from here, you count 1, 2, 3, 4 before you get to it. So from the left, correct. Now, the next thing we need to note is that when you are allocating locants and there are multiple substituents, you now have to consider the order of priority. Take, for instance, now you have this compound. Let's say you have this compound COOH and you have CH3, you have OH, you have amine here. Okay, so with this order, are we going to count from the left or from the right? So yes, quickly answer this question. Are you counting from the left? Are you allocating the locants from the left or from the right? Based on what I just explained, will it be allocated from the left or from the right? Sharp, sharp. Time no day. Yes. Are we allocating the locants from the left or from the right? The left or from the right in this case? So what do we think? Quickly, let's do that. There's no time. Oh. Exactly, from the right. Why? The number of let's list the functional groups here. Okay, so yes, do that for me. What are the functional groups you can see here? Quickly give me the functional groups you can see here. Like for instance, we have the hydroxyl. Yes, what are the other ones? Go on, just put them out there. I'm waiting. What functional groups can you identify? If you can't identify them, then naming will be a problem. So that's why I want you to be able to identify them yourselves. Yes? What functional groups can you identify? I know there's a little bit like of a lag in timing. Yes, still waiting. What functional groups are here? Okay, there is alkanoic acid. Yes, which is the carboxylic group. There is amine, and then there is the hydroxyl. Quite, that's smart. Very good. Okay, so your ability to do that has given you, and then there's the alkyl group. Makes sense. You get that? So this is actually going to help you. However, amongst all these functional group, the person that is ogapatapata, that's the functional group of highest priority, is the alkanoic acid. So we are going to start naming or giving the locants from here. 1, 2, 3, 4, 5, 6, and that's basically how it works. Having said that, let's move on. Now we go to the next rule, which is rule number, is that rule number 4? Okay, no, we've done rule number 4, so let's go to the next rule. Rule number 5. Okay, so rule number 5 says if multiple chains occur as the longest continuous chain, the parent chain becomes the chain with most substituents. I think we have mentioned something like this, so let's go to the next one. When naming substituted alkanes, the substituent is written as a prefix to the parent name with its locant separated from its name by a hyphen. What does that mean? Let's explain that. That's rule number 6, basically. Explaining that is very simple. Let's look at our screen. Imagine, for instance, we have this. We're going to start from like little or less complicated ones, alkanes, before we get into the more complex ones. Okay, so we have Cl. Now imagine we have Cl here now, and they say we should name this compound. Firstly, let's identify the parent chain. As I said, if you identify it, I advise that you put out a circle, just seclude it basically. Okay, so this is my parent chain. Then the next rule is to allocate locants. This is 1, this is 2, this is 3, this is 4, this is 5. Then what is the parent's name? The parent's name is going to be 1, 2, 3, 4, 5 carbon atoms. Because it's single bonds and no functional group, this is going to be an alkane. So what is this going to be? This is pentane. Now that I've named my parent chain, the next thing I'm going to do is to name the substituent. And they said that the substituent is going to be named as a prefix, that is before the parent chain. And what is the name of this guy? This is chloro. But this chloro is located on number 2, so I'm going to put it down as 2-chloropentane. Now there are things I omitted. Okay, let me just see if I can bring them up quickly. Images, let me see. Notes. Okay, quickly, where is my documents? It's not. Okay, okay. Okay, well, I couldn't find it, so I'll just have to say it, so we'll listen and just know it. Okay, so what I wanted to say is this, or the note is simple. Anytime you have a particular name of an organic compound and you have a number as part of the name, the number is separated from a letter by a hyphen. That is to say, you must introduce a hyphen between a number and a letter. I was trying to put it out to the screen so you can be able to write it down, but just have that in mind. You can still write it down that between a number and a letter, hyphen exists. So any name at all, once a number is written and after that number you have a letter, you must put a hyphen between the number and the letter. Now the second point is that a comma exists between numbers. So if I have something like 2,2-dichloropentane, the implication is that because this is a number and this is a number, I have to put a comma sign. You get basically. And then finally, if you have letters, there is no space, excuse me. There is no space between letters when naming. So the implication is that if I have 2-chloropentane, sorry about that. Okay, no, not that. Okay, sorry. Oh yeah, so as I was saying, sorry about that, I had to. Okay, so as I was saying, that between a number and a letter, you are going to have hyphen. But between two numbers, you are going to have comma. And then between a letter and another letter, there is no space between letters. So which means if I write it 2-chloropentane, this is a wrong way of writing it, which means I have to put it together. 2-chloro, and then I put my pentane. And basically that's that. So the principle is this: ensure that you write the locant of your substituent whenever you are naming it. And how do you separate it? You separate the locant from that particular name of the substituent using a hyphen. Remember, there is no space. So in this case, this is supposed to be the wrong way of writing this. This is wrong. Why is this wrong? Because there is a space here. This is not supposed to be existing. You get. And this is correct. Why is this correct? Because there is no space between letters, and between the locant and the letter there is a hyphen. I hope this is understood. Okay, just try this out to see if you understood this. Imagine, for instance, you had this. let's say you had C, 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 and then you had like, yeah, then probably you had BR attached, then this H3, this H2. Okay, so try naming this compound. Yes, try naming this compound. Hope you're still with me. Try naming this compound. What do you think is the name of this compound? Do that quickly so we can move ahead. Do that quickly so we can move ahead. Yes, and that's correct. 3-bromopropanol is very, very accurate, and you have that. Okay, so correct. So let's move ahead. It shows we're actually getting these things. So, having said this, we will go on to a more the next rule, basically. So we'll see if we can round all rules for that today. So that should be rule number, when name is okay, written prefix to the parent name. Yeah, okay, so that's, we're going into the next rule, which is rule number 7. Rule number 7. Okay, so what is rule number 7? Rule number 7 simply states that if a substituent occurs multiple times in a chain, the locant is repeated as many times as its occurrence. Note, appropriate words such as di, tri, tetra, penta, etc. are attached to the substituent to indicate its number of occurrence. Okay, so what does that mean? What does that mean? Let's remove this so we can be able to. Okay, so what that means is simply this. Imagine, for instance, now that you have a structure 1, 2, 3, 4, 5, and then there is chlorine, chlorine, chlorine. If we are to name this compound, first of all, our parent chain, secluding our parent chain, we are going to have that this is our parent chain. This is our parent chain. Then the next thing is to allocate locants. Obviously, you are going to start allocating locants from the carbon atom or the carbon end closest to the functional group of highest priority. That's 1, 2, 3, and 4. Then after allocating it, let's now name our substituent. The parent chain is going to be butanal. Butanal, because there are 4 carbon atoms. And then how many chloro do we have? We have chlorine here, chlorine here. So now we are going to allocate or write this substituent as prefixes. How do we do that? Quite simple. There's chlorine on number 2, so we're going to write 2. There's another chlorine on number 2. You keep writing the locants. So whenever you have multiple substituents of the same substance, just keep writing their locants. So you have 2, 2, 3. Remember, between numbers, you introduce a comma. This is going to be 2, 2, 3. Now, how many chloro do I have? 1, 2, 3, which is going to be trichlorobutanol. So that's the name, basically. So this is going to be 2, 2, 3 trichlorobutanol. Why is this 2, 2, 3 trichlorobutanol? Because 1, the butanol, because this is an alkanal, terminal carbonyl, and then secondly, chlorine is on number 2. Another chlorine is on number 2, and the last one is on number 3. So this is 2, 2, 3 trichlorobutanol, basically. I hope this is understood. I haven't said this. Just try out this one to see how much you understood this. Let's say you have this compound. So yes, what do you think is the name of this compound? So try naming this compound quickly so we can move ahead. Try naming the compound quickly so we can move ahead. Iupac nomenclature is a very broad study, but with these principles, it makes it easier for you to understand the principles of naming. What do we think this is going to be? Yes, still waiting for your answer. Yes, yes, yes. Let's get our answer. Okay, so that's 3,3-dibromopentanoic acid. That's phenomenal. Makes sense. That's cool. Now we are going to actually get into more complicated forms or angles to this, but let's understand the basic rules behind naming them. So that's that basically. Now, I have the final rule we are going to consider. Then we'll now talk about the different angles or complications to these things and probably call it off for today's class. And the final rule we are going to consider is, let me put it up, that's rule number 8. Rule number 8. Okay, so what's rule number 8? As you can see on the screen, rule number 8 states that if multiple substituents occur on the parent chain, they are arranged in alphabetical order as prefixes to the parent name. If you have more than one subject, where you have bromo, chloro, methyl, and so on and so forth, all you need to do is just arrange them in alphabetical order. When you're naming them as a prefix, arrange them in alphabetical order. Okay, so let's take that out so we can be able to understand this. Okay, now let's look at this. Let me take this all out. Now, before I even get to that, I would like to say this, that if you have a group of carbon atom occurring as a substituent, they are referred to as the alkyl group. A group of carbon atoms, a saturated chain of carbon atoms occurring as a substituent, are referred to as an alkyl group. So see what I mean by that. If for instance I have this, if you notice, if I'm to draw out the parent chain, basically the parent chain is going to be circled out as this. Now notice that I now have a substituent here, and this substituent is a chain of carbon atom. Once the chain of carbon atom only possesses single bonds between them, what I'm going to refer to this substituent as is alkyl. Now, the name of this alkyl, when you have two carbon atoms, is going to be ethyl. So I'm just showing you in scenarios where carbon atoms occur as substituents, how do you name them? Once you have a chain of carbon atom occurring as a substituent, and that chain is saturated, meaning that it only contains single bonds, the implication is that it is an alkyl. If it has 2, it's ethyl. If it has 3, it's propyl. If it has 1, it's methyl. Okay, putting out another example, imagine for instance you had this chain, and then you have this basically, and then you have, okay, something like this, something like this. Okay, so once you have something like this, apparently our continuous chain or longest chain is going to be this, which means the substituent here, which is this guy. Okay, let's use a different color for that. Okay, this is now the substituent. Once you notice that the substituent is a chain of carbon atom, and between those chains you have single bonds, you refer to it as an alkyl group, alkyl. But the particular name of this alkyl is 1, 2, 3. 3 means prop, so it's going to be propyl. So just have that in mind, that this is basically how to name saturated chains of carbon atoms that occur as substituents. I'll still talk about those that have double bonds and triple bonds, but first let's understand these ones with the single bonds. Okay, so let's move ahead. Now, okay, before we even get to that final rule, I would also like to say that if you have a name of an organic compound and you notice that the carbon atoms have been condensed, the first thing you need to do is to expand them. See what I mean by that? Imagine you had something like C3H, that's H7, attached to carbon, C, and then probably here you have C5, H11, and then CH3. The first thing you're supposed to do before you start naming this compound, you see these carbon atoms that are together, expand them. The reason you need to expand them is so that you see your longest chain clearly. That's my advice, that when you're naming and you notice carbon atoms put together or compressed together, first thing you need to do is to expand them. We are still going to discuss structures in the next class, basically, and in our discussion of structures, we are going to understand the different ways of identifying the structures of organic compound, the condensed structure, the skeletal structure, and all of those things. But once you look at the structure, this is the zigzag structure basically. But once you look at the zigzag structure and notice that there are carbon atoms put together, before you start naming, I would prefer or advise you to expand it. So how do we expand it? Now imagine, let me expand it. Imagine you have the original diagram is C, then here. Now here has 3 carbon atoms, so I'm going to just expand it or separate the 3 carbon atoms. This is going to be 1, 2, 3. That's all I'm going to do. Then I'll fill the hydrogens, H2, H2, H3. The principle of filling hydrogen is carbon forms 4 bonds, so you count the number of bonds that it has already formed and fill the rest with hydrogen. Then we continue, C, and then continue to here, CH3. But here has 5 carbon atoms, so I'm just going to separate those into 5. 1, 2, 3, 4, 5. I could put it straight, put it bent, put it anyway. The point is just make sure it's continuous. Now 1, 2, 3, 4, 5. Now if you notice with this structure, H2, 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 H3. Someone that counted with this structure might have counted 1, 2, 3, 4, 5, and then say that that's the longest chain, and then be like, this is a substituent and this is a substituent. However, if you expand it, you will now notice that the longest continuous chain will now be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's a whole lot of a difference. So have that in mind, that once you see a condensed group of carbon atoms, it is advised that you expand it before you name. Okay, so I'm going to take this out and then we come back to our final rule. So before we come back to that, let's just look at it once more so that we will have that refreshed. Now the final rule says that if multiple substituents occur on the parent chain, they are arranged in alphabetical order as prefixes to the parent's name. So what does that mean? Okay, it's a very simple concept. Now I'm going to use this illustration. I have this chain. Okay, now if I'm going to name this compound, the very first thing I'm going to do is to identify the parent chain, basically. And before, if you notice, I have a condensed group of carbon atoms. So what am I supposed to do to it? I'm supposed to expand it. So let me just take this out and then expand it. Instead of having it as C2, it's best to write it out as individual carbon atoms so that you avoid confusion. So 1, 2, this H2, and this H3. So let's continue. With this now, I can now count. Remember, carboxylic group is champion, so I must start from him. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. The highest is 6, so I'm going to circle this out. As I said, that's my advice basically. If you really want to get these things, make sure you circle out your parent chain. Now it makes your substituents clear. This is one substituent, this is one substituent, this is one substituent, this is another group, this is another substituent. Now let's get to list out the different substituents. First of all, the parent name is going to be 1, 2, 3, 4, 5, 6, which is hexanoic acid. That's the first thing. Hexanoic acid. The next thing is that I'm supposed to allocate locants. Definitely I'm starting from here. So it's 1, 2, 3, 4, 5, 6. When I'm done allocating my locants, I can now decide to start naming my substituents. Now, I'm noting that, let me just list the substituents first. I have iodine, iodo is iodine. I have bromine, which is bromo. I have chlorine, which is chloro. And I have a chain of carbon atoms. There are 2 carbon atoms attached as a substituent to this chain. So this is going to be ethyl. The principle says that before you attach it as a prefix, arrange it in an alphabetical order. So this is not in an alphabetical order. So let's have the right order. The right order is just simply read ABCD. A, B. There's no A here, but there's a B, bromo. So bromo comes first. When I'm done naming bromo, I go to chloro, because after B is C. Chloro. And then after chloro, I go to ABCD E. E, ethyl. Before I now finally go to iodo. Okay, imagine for instance, let me just complicate this a little bit and add another bromine here. Probably add chloro here. Okay, so let's get to work. Now, if I'm to name this, I will start by naming all the bromos first. And what bromo? I have bromo on number 5. I have bromo on number 3. So that's going to be 3, 5. How many bromos? Dibromo. Then I continue naming chloro. Chloro is on number 4 and chloro is on number 2. So that's going to be 2, 4 dichloro. Okay, and then this might not get fitting. Okay, let me remove this for now. We remember that it's hexanoic acid, so have that in mind that it's hexanoic acid. We would actually come back to put it in the name. Let's just outline alphabetically our different substituents. So we have dichloro, 2,4-dichloro. After I have named chloro, I've named bromo, I've named chloro, I go to ethyl. Ethyl is located on number 3, so that's going to be 3-ethyl. And then I have ethyl gone. There's no other ethyl. The last one is iodo. Iodo is located on number 5, and that's going to be 5-iodo. So notice that I have checked out all my substituents. Did you notice that I arranged it first in alphabetical order? So after that, I can now attach my parent's name. The parent's name is hexanoic acid. So this is going to be hexanoic acid. Please notice this. Between number and letter, hyphen. Between number and number, comma. Between a letter and a letter, there is practically no space. So you just have that in mind. So the name of this compound is going to be 3,5-dibromo, 2,4-dichloro, 3-ethyl, 5-iodo hexanoic acid. I hope this is understood. So yes, any confusion? Any confusion? Any confusion? Any confusion? Yes, please indicate so that I will know. One response and I continue. Any confusion? Just one response and I continue. Any confusion? Just one response and I continue the class. Okay, so without wasting any more time, I will now highlight some of the confusing parts or some of the things that can make naming confusing for us. Before I give you your own examples to do. Now, the very first thing I would like to highlight is this. Double bond representation. How do we represent double bonds when we are naming? It's quite simple. It's quite simple. When you are going to represent a double bond, let me just put it out so that so that everybody can see it. Basically, if you are going to name a double bond, this is how to name a double bond. Basically, if a multiple, that's when I mean double bond, I mean double bond or triple bond. That's generally talking about multiple bonds. So if a multiple bond is indicated, the lesser locant is indicated in the name. The locant is placed either in front, which is before or in between the name of the organic compound. Okay, so let me explain what I mean by this whole thing I just said. Take for instance, let me take this out. Take for instance, you have that your organic name, organic structure is this. Based on the principle of naming, what we just discussed, let me ask a question. The question I'm asking is, from what end am I going to start allocating locants? Is it going to be from the left side or from the right side? So let's start with that. Yes? Yes. Where am I going to start allocating locants from? The left or the right side? Locants are going to be allocated from what side? Left or right? Left or right? Yes? Right, exactly. Now, the simple reason is because carbonyl group is above alkene in the order of priority. So with that, that is the first thing that has to be removed as a confusion. So 1, 2, 3, 4, 5. Now let's name this particular compound. We have 5 carbon atoms, which is pent. But because you have a double bond, it will not be pentane. That is pentan. It's not going to be pentan. Why? Because you have a double bond. Double bond is represented by the suffix ene. So which means this is going to be a pentene. Now, but you need to indicate where the pentene is located. That is to say, where the double bond is located. And how do I indicate where the double bond is indicated? It is between 3 and 4. Please, when indicating the locant of a double bond, indicate it. The number you are going to take or the locant you are going to take is the lesser locant. So this is going to be pent 3 in. But I'm not going to put the E because I'm going to replace this E with the final or the major functional group, which is al. And this is going to be pent 3 in al. It's confusing, but I hope this is clear basically. First of all, proper allocation of the locants. Then when you come to a double bond, you need to indicate it as in. Instead of pent an, you say pent in. If there was a triple bond, it will be pent in, basically. So in this case where we have a double bond, between the two numbers, you are going to take the lesser locant of the carbon double bond. That is what that note is basically trying to say. I hope this is clear. Is there any confusion? Any confusion? Any confusion about this? Any confusion? Yes, there's a lag in time, but yes, please comment. Okay, very good. Okay, so because there's no confusion, you try this one. Imagine, for instance, you are giving this instead. Let's see. You try this one. Let's see. You have OH here and triple bond here. Okay, then this is H3. H2, H3. Okay, yeah. So, what do you think is the name of this compound? What do you think is the name of this compound? You try this. Oh, yeah. Oh. What do you think is the name of this compound? Okay. So, do that quickly. Okay. What do we have as the name of this compound? Still waiting for your answer. hexane 3 or. Okay, I think I'm going to come in here. Now, it is going to be hex 3-ine. Hex 3-ine. You write the locant before you indicate whether there is a multiple bond, basically. So if you notice, when we said pent, I think it was pent 3-ine. That was what we used. I will get to that exactly. So with that now, very good. I like that question because that was what the next thing I was about to explain. Now, if the question she asked was how will I indicate the position of OH? Very simple. Now, if I'm to name this compound, I know it's hex. That's the first thing. And I know there's a triple bond, which is ine. This triple bond, I'm allocating locants from this side because OH is above alkyne. So it's going to be 1, 2, 3, 4, 5, 6. So this is going to be hexine, right? So hex 3-ine. But I'm not just going to put all. Where is the all located on number 2? 2 all. So this is the name of this compound. Hex 3-ine 2 all. Any confusion? Remember, I take it again. Now what I basically did was hex for the 6. Because there is a multiple bond, I have to show where the multiple bond is before I continue. So that's 3 and the multiple bond is ine. Now, having indicated the multiple bond, I now go to the final part, which is the suffix, the main functional group here, which is alkanol. Where is the all located on number 2? So this is hex 3-ine 2 all. I hope this is clear. Okay, very good. Okay, you try this. You try this one. You try this one before we get to start rounding up things. You try this. Imagine you had something like okay, 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 and then you had like Cl. Okay, so try naming this compound. This is going to be like H. Yeah, just H. Yeah, and H3. Okay, so what do you think? Try naming this compound. Remember, this is not carbon, this is chlorine. So try naming this compound quickly. Let's see what comes out of it. It's a very, very confusing thing. But just follow the principles, basically, you will get your answer. Know the functional groups, then allocate carbon atoms properly, circle out your major functional groups. What do we think? Iupac nomenclature will follow us throughout our study in CHEM122. So it's important you know how to deal with that. Okay, makes sense. 5,5-dichloropent 3. You know that's supposed to be, it's triple bond now. It's ine, not in, but yeah, I think that should be an error, right? It's triple, unless you can't see it clearly. It's supposed to be like 3 lines. You get, so that's ine, not in. Triple bond is ine. Okay, but yeah, very good trial. Between 3 and 4, correct. So if you had written sorry, let me be sure that this is okay. Yes, so if you had written, let's allocate the locants. Circle out first. I like circling out. I like circling out just to be sure. So allocating locants, this is 1, 2, 3, 4, 5. So the parent name is going to be pent. It's going to be pent. But this pent has triple bond, so it's pentine. Where is the ine located? It is between 3 and 4. So pent 3 ine. And then I have that the major functional group is alkanone, so which means ONE. Now, but then, as you indicated, The alkanone is on the second carbon atom, so this is going to be pent 3-ine 2-one. Having said this, my substituents have not been attached. And how do I attach them? There are two of them, which is 5,5-dichloro, 5,5 dichloro pent 3-ine 2-one. Basically, I hope. Okay, so that is clear, right? Good, very good. Okay, let's just try one more technical one before we probably call it off in today's class. A margin. Let me just make it a little bit tricky. Now imagine you had, if you had something like this and you still had OH, automatically this OH will not reflect as an alkanol. It will now become a substituent, hydroxyl. You get, once you have that, you have two major functional groups. The major one, two functional groups I meant to say, the one with the higher priority will be part of the parent name, while the other one exists just as a substituent, and this will now be the substituent hydroxyl. So just have that in mind in this particular compound. Okay, so let me just put up things. Okay, so chloro, this is H2, 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 H3, bromo, and then let's not make it very confusing. But let's just put one more, just one more. Are you doing? Make here H3. Okay, yes, name this compound. Name this compound. This is the final compound we are going to be naming for today. Then continue tomorrow. Yes, there's going to be class tomorrow, so yes. Oh yeah, attempt. Try naming this particular one. If you're able to name this, then it shows that you have been following the class well. Yes, still waiting for the name. This is the final name for today. We'll continue naming and structures tomorrow. Oh yeah. Any ideas? Oh yeah. Remember I said that because you have hydroxyl and carboxylic becomes the major, which means hydroxyl will now be a substituent. It means that you are going to name it as hydroxyl as a substituent before the parent name. So just have that in mind. Okay. This is the final name for today's class. Do that quickly. Okay, still waiting for the name so that we can call it off for today. Abi, is it confusing? If it is unnameable, just talk. If you feel you can't name it, just talk so that we would move ahead. If you're confused, just say you're confused. I'll name it, then call it off. Okay. If I wait past 3 minutes, I'll name the compound. Okay, I think you have something for us. Let's see. Let's see. Okay. So let's see. 5-bromo 4-butyl. Makes sense. 5-bromo 4-butyl 2,2-dichloro. That should be 3-hydroxyl 4-iodo hex. Okay, now see the problem. Hex 4-ene. I think that's what you wanted to do, is hex 4. You should indicate the ene. Hex is just for 6. Hex 4-ene oic acid. I hope the correction is, you've taken note of that correction. Onyekachi, hope it's clear. Hope you took note of that correction. So let's put this name together. Just take note of it. You said hex 4 noic. No, it's hex 4. Then you say ene. You are indicating that there is an alkene there, which is the double bond. Okay, let's put the name together. First of all is my parent chain. I have to circle it. I could have counted these ones, but you notice that there are more functional groups like this. So this becomes my parent chain. If I count like this, is the longest, yes. However, we said that when counting, that you should count the longest chain that has the most number of functional groups. If I count like this, it doesn't make sense. So I have to count straight up. So with that said, circling my parent chain, remember, it must contain the functional group of highest priority and as many other functional groups as possible. So with that said, if we are going to name this thing, allocating locant has to start from here. 1, 2, 3, 4, 5. So putting the name together, all the substituents I have here, I'm just doing this for the sake of others. We have, you are correct, Kachi is correct. We have bromine, we have iodine, we have OH for hydroxyl, because it's not a substituent because you have a higher functional group. So once you have a higher functional, the others become substituents basically. We have chlorine. Then we have this chain. This is 1, 2, 3, 4. 4 is butyl. Once you have a chain of carbon atoms, saturated chain of carbon atom occurring as a substituent is an alkyl, and in this case is butyl. So butyl, I don't think there's any other thing. This is butyl, bromo, iodo, hydroxyl, chloro. Yeah. So arranging this in alphabetical order, that's going to be, we have 2 B's, but you will notice that B and B are the same. So you go to the next letter, arrow comes before you. So you have to know your A, B, C, D. A, B, C. Then we go to butyl. After butyl, chlorine. Chlorine before iodo, right? Oh no. A, B, C, D, E, F, G, H is hydroxyl, not, you know, some of you might just confuse this as OH, but this is hydroxyl. So H comes before I, so hydroxyl. Then we have our iodo. So naming this thing down, this is going to be oh no, this is 6. Thank you. So this is going to be 5 bromo. Then we go to butyl, 4 butyl. Then we go to chlorine. There are 2 chlorines here, so that's going to be 2,2 dichloro. And after chloro, we find the hydroxyl, 3 hydroxyl. And after we've gotten our hydroxyl, we now have iodine, 4 iodo. Then we go to the parent name. The parent's name, this is a carboxylic group, so this is going to be an alkanoic acid. So this is going to be 6 is hex. Iodo hex. Now there's a double bond, so I need to show where the double bond is. Hex 4-ene. Ene is for double bond. If it was an alkane, it would be hex-an. You don't need to indicate. If it's single, there's no difference there. So hex 4-ene. Then what is the suffix for the carboxylic group? In oic acid. I hope this is clear. Okay, so that's that basically. We're going to be calling off the class for today. Remember, this is Waits Lounge, Learning Made Easy. We're going to continue the class tomorrow. For those of you that were not able to attend the class, do join the class tomorrow. Don't forget to like and subscribe, basically. Thank you very much for joining our class.